So, thank you, Andrea, for the introduction. And okay, I will describe a little bit about correlation. You have seen this picture taken from Kirenburg, one of Kirenburg paper. These are the large variety of functionals that we deal with. They are more or less organized actually in families, let's say from the simple, depending on which ingredient you try to include in the description. And so there are the simple LDA functionals or local spin density functionals that depends only on the local density. Then, since this is not enough, people in the 90s introduce gradient corrected functional, generalized gradient corrected functional. Then they introduce also kinetic energy density ingredients, and then they introduced hybrids or in which the wave functions, the functional depends on the individual single particle orbitals or on the excitation spectrum, and then they go through RPA and more complicated functional. So in principle, there is a, let's say, this Jacob Lauder picture of density functional theory, which is, let's say, a trademark, registered trademark from John Perdue has, let's say, invented this scale, this ladder that should bring us to chemical accuracies. But each, let's say, round of this ladder has been introduced for some reason to solve some problems. So at the beginning, everything was very happy. Everyone was very happy with the LDA. They started with the Oerenberg-Kohn theorem that say there is a functional. Then if the functional is, however, complicated because describe kinetic interaction, correlation, and so in 1 year later, Kohn and Sham introduced their non-interacting auxiliary system, which describe correctly in this theory the kinetic energy, which is a major part of the energy. And so then you can also, of course, calculate the Hartree energy, which is a major part of the interaction. And so you can kind of define exchange and correlation as the difference between the unknown functional f and these two terms that you can compute. And so you're left with an unknown functional that you call exchange and correlation functional, and from which you can obtain a definition of the energy, a definition of the variational principle, and for the cell-consistent Kohn-Sham problem, in which, in principle, this is a solution of the problem because it's a mean field-like approach, which is in principle exact. The problem is that the exchange and correlation is not known, and so this actually leads to the approximation. Why you can hope that this is a good idea? Because the exchange and correlation energy is a small fraction of the total energy. So, I mean, if you take, this is an atom, I think, manganese, and if you do Hartree-Fock for manganese, you see that the largest part of the energy is the electron-ion interaction. Second largest is the kinetic energy of the electrons, Hartree-Fock theory. Then you have the electron-electron interaction, and then exchange. The correlation is not included in Hartree-Fock, is actually smaller than exchange. So you can hope that making approximation for these things is better than making approximation, for instance, for the kinetic energy. And this is basically the reason why we try to introduce approximation for this. So the other way around. And so the first system, the first approximation that was introduced immediately in the Kohn-Sham paper 60 years ago is LDA, in which you say, okay, we write this exchange correlation energy as a sum of local terms in which each small volume of the system will be assigned an energy which is the energy that you would have in a uniform gas. And of course, this will not be a completely faithful description of reality, but hopefully, if the inhomogeneity can be neglected, the knowledge from the homogeneous electron gas will be useful. And this was fine. People were happy for a while, and we had energetic stability. I mean, many things can be computed and were reasonably satisfactory. In general, the results that you obtain are superior than Arc Fock. So in this sense, people were very happy at the beginning. There were problems, but also energy transfer between different energy level in atoms were better than Arc Fock, and compare better with the experiment than Arc Fock. In general, what happens, the geometry is relatively good, a little bit bond lengths are typically underestimated, binding energy are typically overestimated. One deficit that was very soon realized for LDA, and so lattice constants of bond lengths were typically too short, cohesive energy typically too large, correspondingly Bark moduli or stretching frequency a bit too strong. Band gaps are too small, but this is not a problem of the functionality problem. So people, after the first, I don't know, 10 years of excitement about LDA, they started finding systems in which things were not working well. And so they introduced gravity-corrected functionals. The reason is that if you, for instance, you look at this is charge density of beryllium atom in the radial direction, and the density, okay, has this shape is decaying. If you calculate these reduced gradients, so the gradient of the density divided by the density to the 4/3, since the density decays exponentially, basically this ratio, which say is a measure of the inhomogeneity of the system, has some reasonable value, finite value in the majority of where there is a lot of density, but actually when the density is decaying, this inhomogeneity parameter basically diverge. So it's clear that this region is not may not be well described by the LDA potential only, and so people introduced the first few of the hundreds of gradient-corrected functions that have been introduced in the last. And what you basically write is an energy, the exchange correlation energy is an object that is typically also decomposing spin up and spin down contribution, in which you have a uniform, so LDA-like term that multiplies an enhancement factor. And this enhancement factor is parameterized in different way. One problem with the GGA functional, and in general, all more sophisticated functionals is that they are under constraint. I mean, we have physical constraint that we want to satisfy. Some of them are typically enforced, but there is much more variability in the functional than constraint that we can impose. This is at variance with LDA, where instead, if you choose a model, which is the uniform electron gas, you have only one parameter, the density, and so basically LDA is the only ab initio functional that exists because it can be computed from the quantum Monte Carlo calculation of the exchange correlation energy in the uniform electron gas, and this is one function. There is no doubt of what is LDA. Why? Depending on which version you pick for the function and all the other functions, you have many choices. These choices, Perlu 191 at the beginning, and then TB, which is a very popular one, they improve the problem of binding energy. So binding energies, lattice parameters and bond lengths more or less remain similarly accurate, but there is an improvement in the binding energy compared with and these go across several systems. So in general, if you put together the two things, the lattice parameter are LDA a little bit tends to underestimate, GGA tends to make them overestimate a bit, but more or less they are all okay. Cohesive energy is much better for GGA, and similarly, things are less bound, and so also the bulk moduli tend to be a little bit softer in GGA than in LDA. But overall, there is a big increase, big improvement in the binding energy, and this basically is the reason why we are here. And GGA was important to fix some major problem for magnetic system, like iron was not magnetic in LDA, while it is magnetic. Okay, right. And if you calculate, either compare different structure of elementary materials, you find that GGA is the correct ordering of the function of the different structures. Right. So iron in LDA was not magnetic, while instead it becomes magnetic. Okay. So I very quickly went through LDA and GGA because we want to look at different. So what are the problems left? Well, okay, although GGA is better than LDA in terms of binding energy, we are still far from chemical accuracy. Trends are typically good, and but weak bonds are problematic. And this difficulty stems from basically two major issues that David already mentioned. One is that there is an imperfect treatment of the self-interaction energy. So in R3-Fock by construction, we have self-interaction cancellation. But if you replace the Fock operator that is built to cancel self-interaction with something that includes approximately correlation, but also approximately treat the exchange, then you are kind of losing this exact cancellation. And for some systems, this may be not relevant. For other systems, it may be important. And for instance, when you want to look at dissociation, the dissociation limit of molecules, or you have transition metal oxide or rare earths, or other system in which the atomic nature of the levels that you are so strongly correlated system in which the atomic nature of the wave functions is very important. So you have very narrow bands, etc. These are regions in which self-interaction may be very important. And so the fact that the function that we are using treat them approximately may have a large impact. And another defect, let's say, another shortcoming of the function of the simple semi-local functionals that we have is that van der Waals interactions are not taken into account, and van der Waals is everywhere. I mean, it's an kind of interaction that is everywhere. Very important when other kind of interaction, stronger kind of interaction like electrostatics are not present or less important, but van der Waals is always there. And when you deal with organic molecules that are typically neutral and closed shell, etc., then this is basically what is left. And then if you don't treat it correctly, it's a problem. So these are the two types of problems that require additional, let's say, thought going beyond LDA. So I will, I think, skip about meta-DGA, which is also interesting, but I think I don't have time. And so let's talk about addressing the self-interaction error and what are the tricks and methods that people have tried. Historically, the first one go back to Perdue and Zunger, actually, their paper where they introduced the Perdue-Zunger LDA approximation that we used at least at the beginning. Actually, that functional is in an appendix of a paper that is dealing with self-interaction correction. And where they basically say, okay, what is the reason, what is the problem with the self-interaction correction is that you have systems in which, so suppose that you have some electrons, and these electrons may be exist in a metallic, so takes a metal and use the metallic phase or the oxide phase of this element. In one phase, the density of state is going to be very broad. The electrons are going to be delocalized on a large portion of the real space, and therefore the self-interaction energy is going to be relatively small. Instead, in the oxide, some of these electrons may localize around the side or around the transition metal cation, and therefore the electrons are much more localized and therefore has much more larger self-interaction. Of course, if the self-interaction was treated correctly, everything is fine. But if you have some error in the self-interaction, you may likely do different errors when the orbitals are very localized and when the orbitals are very, very delocalized. And therefore, this may impact the predictivity. So basically, the fact that you may have the same element in different phases in which, in some of which you expect a small self-interaction, and in others in which you expect large self-interaction, since you treat this inaccurately, you may expect this to have an impact on the result. Okay, and for instance, if you study simple redox reactions, if you think that you are adding some phosphate, I mean, you make some combine and you add lithium to one of these other transition metal oxide, of course, the extra electron that lithium provide is metallic on one side and instead transferred to the localized orbitals on the other side, and GGA make a significant error in predicting these energy information energy related to the fact, mainly related to the different treatment of the self interaction in the two cases. Okay. So, what is the problem? The problem is that if you have narrow bands, if you think that you have two levels, two atoms, and that are weakly coupled, so that the transfer, the coupling between these two, the Hoping term between these two set of orbitals is relatively small, so that the bandwidth associated to these levels is small. LDA treat this as a non-interacting system. So basically, the electrons are going to be distributed with some phase between the two sides. But let's say that this transfer, this Hoping terms is related to the overlap between the two orbitals, and so this, if the shape of the wave functions is reasonably correct, this is okay in LDA. What is totally wrong in LDA is that when you happen to have two electrons on the same side, or when you have two electrons separate in the two, one in one side and one in another side, this is completely different if you include correlation. So if you include basically self-interactions. So the fact that when you have two electrons on the same side, the second electron interacts with the electron that is already present, but does not interact with itself. This is not taken care correctly by LDA. And so if the localization of the orbital is large, then treating it at the LDA level or GGA level is not too big. So what can you do for that? And for instance, in iron oxide is a transition metal oxide, which is an insulator by nature. I mean, and instead it ends up with a metallic phase in GGA, related to the fact that the 3D orbitals of iron are partially occupied. So across the bandwidth, the region of energy that the narrow region of energy that right. So how you deal with this? In the original paper by Zunger, they basically said, let's impose force the system to satisfy self-interaction energy, self-interaction cancellation when we deal with a single orbital. So the fact that for a single orbital exchange energy should cancel exactly the Hartree energy. This leads to a theory which is orbital dependent, complicated. I think conceptually was important, is important to because they clarify what is the problem, but computationally is not particularly practical because you end up with an orbital dependent theory. Another way is to go in the direction of hybrid functionals, because we said the problem was not present in Hartree-Fock. So let's go back to the origin, and let's include back Hartree-Fock in the game in order to treat exactly or more correctly this self-interaction problem. Or and then maybe this is what we are going to discuss more in the next days, this DFT plus U method try to address the problem of the basic problem of this self-interaction, which is that when you have a systems that are isolated, the energy as a function of the number of particles that are assigned to that system or subsystem, the energy should vary linearly, piecewise linearly, with the occupation of the fragment. So DFT plus U, in a certain sense, is built, can be built to satisfy this, and has been, and can be more efficient than DFT. Okay, so this is the paper 1981 dealing with self-interaction correction by Zunger. And basically what they say is that whenever we have our function is kinetic energy plus R3 plus the exchanging correlation, and the exchanging correlation is modified from the approximation plus a correction. And this correction is built by basically for every single orbital, you remove the R3 energy corresponding to it, and you put it back, and you remove the approximate exchanging correlation energy for that orbital. So in R3 Fock, these two are equal and opposite, and delta is 0. If you have an approximate functional, this is non-zero. By removing this error that you make, so this is basically the error that you make at the single particle orbital level. If you use an approximate exchanging correlation, you remove this, and in principle you are self-interaction free. But you end up with a functional that depends explicitly on which orbital you decide to choose to occupy, and is going to be is complicated. But let's say has this is the problem that is trying to solve. Another way to see the problem is to start a bit more ab initio, and try to see how this leads to hybrids. Okay, what we have is that we have the problem, initial problem, Hubbard and Koopmans fully interacting system is defined by a kinetic energy, the electron-electron interaction, the external potential. The non-interacting Koopmans system is defined by, is the same basically, except that we don't have interaction. And what is particular of these two, what link these two systems is that the density is the same. You can think of not just these two systems, but of a family of systems defined by a parameter lambda, in which the interaction is multiplied by lambda, and for every value of lambda you have an external potential, and this external potential is such that for lambda equal 1 is the external potential, for lambda equal 0 is the Koopmans potential, and for and the important property that all these systems have is that the density that they produce at the minimum is the same. So basically, we are switching on or off adiabatically the interaction, keeping the same density. And this we can do, and for each of these value of lambda, there is a variation. And so there is a variational principle, and this variational principle makes that we can calculate the derivative, and since it is a variational system, you have a kind of Hellman-Feynman theorem that apply, and eventually if you take the derivative and integrate back the derivative from 0 to 1, you can write the energy of the interacting system or the energy of the non-interacting system plus something that include the integral from 0 to 1 of some average interaction energy. And if you work out the equation, basically you have that the exchange correlation functional plus the Hartree energy, which is trivial to compute, is related to this average. So it's the average between 0 and 1 of the interaction energy computed over the ground state wave function, from the ground state wave function of the non-interacting system to the ground state wave function of the fully interacting system. Okay, and this led basically Becke to say, okay, so this is what we have. We have the expectation value of the interaction between 0 and 1. Well, but in 0 we know what it is, because the non-interacting wave function, the energy, interaction energy of the non-interacting wave function, we know how to write. It's basically Hartree energy plus the Fock energy of those non-interacting wave functions. So basically, this is the Hartree Fock energy. I mean, cancel, so lambda equals 0, contribute the Hartree energy and the Fock energy computed with the non-interacting wave function. And then you should, in principle, if you do trapezoidal integration, it is basically 1/2 of what you have in 0, 1/2 of what you have in 1, and then you approximate what you have in 1 with something, because you don't have anything, you don't have exact knowledge. So if you, for instance, you use LDA or GGA for that, and then you end up with something that in the 92 Becke called 1/2. And it was the first hybrid. Then things were evolved, and this parameter of how much Hartree Fock you include became a parameter, and this parameter was 20%. In V3LEAP, it is 20%, and it is, and then you have some parameterization for the rest that you fix in this, basically fitting results for a number of molecules and then fixing the parameters so that to minimize the error in the thermochemistry for this benchmark systems. V3LEAP was kind of defined this way, and it's very popular among chemists. Perdue and co-worker didn't like the empirical nature of that thing, and so they had some argument to say that actually they expect some behavior, and then they have some argument to say that actually the fraction of Hartree Fock that is appropriate is 1/4, and then for the rest they use their favorite functional, that is PBE, and then this is PBE 0. Okay, and then enter Scuseria and the co-worker enters, and they say no, but okay, we know that I mean, we can make a range separated functional, and so we use Hartree Fock, but only for the short range. Also, this helps in the convergence, I mean, in the expense of the calculations, etc. So there are additional parameters. You see that you have good reasons, physical reasons to impose different constraints or different requests, or to fit a different data set, and then with this you fit a few parameters, and then of course depending on which system you choose to reproduce, and you may have different parameterization. So, but in the end, some of this functional became popular, and PB0, Bitry-Leap, and half-half not so much nowadays, but Bitry-Leap, as you see, are popular, and as well as among the gradient corrected functions, PB-solve, and similar are de facto the winners, but it's because people need to choose something at a given point. You cannot keep testing new functionals always. Okay, this is, I think I will skip something that say, okay, this is Artifoc. Exact change is not Artifoc. Exact change is in principle Artifoc computed with the Constant orbitals, which are different. They are slightly different, but they are different. And in principle, when you deal with hybrids, you should do OEP of, so you should mix whatever correlation terms you want with the exact change. What we do actually is to mix with Artifoc, because it's simpler, because solving the exact the OEP equation is a bit of a mess, but anyway, Artifoc, even if you include a small fraction of Artifoc, is going to be very, very expensive. I don't like that. And you need to deal with the divergence may appear. And let me, but you get compared to PW, compared to PB, you get better accuracy compared to many molecules in this particular case, a few more. So PB0, okay, Artifoc is terrible, PB is better, PB0 is more expensive, but because of the expensive. And the scaling so another alternative to deal with this sorry, what time is it? Okay. Another alternative is to use this LDA plus U energy functional that again was introduced in the 90s as in a different context, people that were dealing with transition metal oxide and strongly correlated system, they introduced this U parameter to describe the Hubbard U that is needed to describe this this kind of systems. So as an approximation of the Hubbard model that is appropriate to describe the strongly correlated materials. In the end, in the way I understand how this LDA plus U works, it is a way to restore this piecewise linearity that you have between when you have electrons that are shared between different fragments. So what? So in principle, if you look at the paper that introduced it, it's a complicated things. They write it as a kind of restricted Artifoc projecting on orbitals of certain orbital manifold localized orbitals around certain atoms. In the simplest rotational invariant version of this in this theory, it is simply a constant that multiply the density, so the projected density over the orbitals we are dealing with for the atom I and the spin sigma. is the trace, so the excitation value of this density projection times 1 minus the density projection. And then if you go in the eigenvalue basis of the matrix, of the occupation matrix N, this is basically a sum of contribution in which each orbital that corresponds to the eigenvalue of the occupation matrix is penalized by a parabolic cost, let's say, that is higher when the orbital is half occupied, and instead goes to zero when the orbital is completely empty or completely zero. So basically, this is an object that, depending on the strength of view, discourage partial occupation of the orbital. Which orbital depends on the system, and it depends on the geometry on which are the right eigenvalues, eigenvectors to deal with. Depends on the system, but once these orbitals are chosen, the effect is that basically partial occupation of the orbital is discouraged. Why this is relevant? Let's go back to what we expect and what, let's say, self-interaction correction should describe. I mean, if we are describing correctly self-interaction, what we do expect? We do expect that if we have two systems, two atoms, suppose two separate atoms, and we have to distribute electrons among these atoms, and then we can distribute an integer number of electrons to one atom and an integer number of electrons to another atom, or we can distribute partial fraction of these electrons to the different atoms. In the real system, these are separate systems. The energy of a system with fractional occupation is so there are never a fraction of electrons on a system. There is an integer number of electrons for a fraction of time in the system. And so basically, when we say that one atom has n plus 25% electron, this means that 25% of the time it has the energy E n plus 1, and 75% of the time it has energy E of n. So basically, you expect the energy to be a piecewise linear function in which the slope of the linear terms are related to the Yana theorem, and so are related to the last occupied orbitals, which DFT should produce correctly. And it is the ionization energy if you are removing the electrons, and the electron affinity, negative of the electron affinity if you are adding the electrons. This is exact. I mean, qualitatively, but this is what you expect for the exact theory. And if you do LDA, GGA, or even hybrids, you will get another curve, which is going to be continuous. And so you see that what you are missing, let's say, in order to describe this system correctly, is something that looks like a penalty in the approximation in which this curve is simple, it's just quadratic, is something that looks like the DFT plus U correction. Of course, you need to compute this U, and this U is what? This U is, in this simple case in which the atoms are fully very separated, is the wrong curvature that the approximate functional has, because what you should actually have is something which is linear, and so there is no second derivative. So basically, this is the idea. behind computing the U in the DFT code as well. And it works in the sense that if we do this calculation as we saw before, side on side, where these three d orbitals are all mixed and it's difficult to entangle them, if you add this penalty with the proper amount of U, this group of bands will be split. One will choose to be totally occupied, two will choose to be totally empty, and there will be a gap in between. This happens also for other systems in which there are strongly localized orbitals. So like in cerium, cerium is a rare earth, and so has 4f electrons that can be in the delocalized mode if you do LDA or GGA, and if you include plus U, you can manage to basically split off one of the level that is going to be totally occupied and the others that are going to be totally empty. How do you compute this U parameter? You will have, I think, more about that in the next days. But basically what you want to compute is what is this fake, what is the wrong curvature. And the wrong curvature is the wrong curvature due to the interaction. But there is also a term coming from the fact that when you move around the orbital levels, they also redistribute for just hybridization, normal hybridization. So this gives a contribution that has nothing to do with correlation or the functional. So basically you calculate the curvature associated to the change to the functional, and you remove the contribution that is due just to the fact that moving around the levels, you redistribute the electrons a bit. And this is the paper by Matteo and myself. And okay, I don't enter in these things. I think it will be presented more in details another time. And instead, I would like to finish discussing the other problem, the other big problem, which is separate, has nothing to do with such interaction, but is what you do with van der Waals. Because van der Waals is a truly non-local effect, and in the last 10 years, people have worked a lot, maybe more than 10 years at this point, to deal with it. And again, it's everywhere, and it's due to fluctuation. So you have, again, you have two fragments, and even if the two fragments have no finite charge, still they interact, and they interact because a fluctuation of charge, fluctuation of charge. Even if you have two neutral atoms, a fluctuation of charge on one side will induce an electric field on the other atom, which will respond with the quantity which is proportional to its polarizability, and then a decay that is r to the -3, because this is dipole interaction. But then this dipole will interact back with the original fluctuating dipole, and so in the end, you end up with something which has to do with the pair of polarizability of the two fragments, and has a typical decay for small fragments that is r to the -6, which is what we know about the interactions, Heitler-London type interaction. Is this something? Of course, LDA, GGA, Hartree-Fock do not describe any of this. This is a correlation effect. This is a correlation effect, but in principle is a correlation effect. So it's something that the density functional should be able to describe. Only that it is a non-local density functional. And so there have been several attempt to deal with these systems. And in LDA, we write the energy as a local. So we concentrate on what happens around one point. In GGA, we do with a more complicated kernel, but it's always concentrated around one single point. What you need in the case of and therefore, since they focus on a single point, this is not able to describe van der Waals because it is a truly non-local effect. One can show that even hybrids or RT-Fock does not describe this kind of non-local interaction. And this may have a big effect. For instance, if you do calculate the graphite geometry in with GGA, semi-local functional, the in-plane lattice parameter is spot on the experimental value. The out-plane, so the C over A prediction is completely wrong. Very, very shallow minimum and very, very high wrong parameter, because the interaction between the graphene sheets is basically van der Waals, and it is not well described. It's not described by GGA function. Okay. So what we do with that? For decades, we just forget about. We were dealing with strong bonds, semiconductors, oxides, and where van der Waals is present, but it's negligible with respect to the rest, and so we don't care. But the more and more people are interested in organic systems in which van der Waals is what is left after you are kind of, you have closed shell element molecules in which electrostatics is more or less dealt with, and then what is left is van der Waals. So there have been different methods, some empirical one, so Grimme, very popular, D2, D3 are methods that add basically an empirical damped dispersion correction. Tachenko-Scheffler similarly is, they claim to be more ab initio, but still they add an extra term. They have a functional which does not describe van der Waals, and they add extra terms that contains the van der Waals interaction. But in principle, they are not very consistent because van der Waals is a correlation effect, so should be in the exchanging correlation function. And so Landgraf and co-workers, Swedish co-workers, have developed functionals in which basically they try to describe this non-local interaction. And again, they started with one function they call VDVDF, then they have a second version, then someone else introduced, Vidruf and Gomburis introduced some simplification. And so now I think, I don't know if there are more that are coming out here, but basically these are the ones that the most popular one. And then there is a lot of work related to what exchange you add on top of this, because this describes the correlation, and then, but then there is of course compensation or not compensation of errors between the correlation and the exchange part. Or one can go straight to the most ab initio methods and try to deal with this interaction at the RPA or beyond RPA levels, but this is very, very expensive. So this is, okay, you neglect, it's fine, but you forget about organic systems, so this is not a good choice anymore. These are successful. Grimm is successful many times. To me, is a little bit unsatisfactory because it's not, I mean, should be a density functional term, it is just an add-on to the theory of a functional that does not include it. So it's a kind of double counting because the functional should contain it, but since it's doing a bad job, you add something else that describe it, but it's kind of admitting that you are not describing the proper physics in a certain sense. This has the ambition to be functional, and it is reasonably accurate, I think. And so, okay, Grimm and company basically add extra terms that depends on these interactions coefficient, which is related to the atomic polarizability of the fragments, and they have a number of scaling factors that are fitted to in order to reproduce a bunch of systems, so that they are basically accurate for a number of representative systems, and they reproduce high-level calculations. This is Schenker-Scheffler, which is a more complicated method, but again, is something in which you write for each fragment, you write a term, and some of these coefficients are calculated from the electronic structure of the fragment, and so in a sense it's less empirical, but still you are putting together ingredients coming from different objects, but still they are able to reproduce reasonably well the interaction between a number of fragments. The van der Waals-DF root, let's say the van der Waals-DF idea is that this is a non-local functional, so it has a kernel which is so that couple two different points in space, and the kernel is, however, a function, a full function of the different positions of the distance between the 2 points, but also of the description of the 2 environments, and the description is given in terms of the density and the gradient of the density. These are the original paper by the Radker-Kalmers group, and Vidius van Voorhis later on proposed some refinement or some variation. Yes, I'm finished. I'm done. And these are non-local functionals, and basically one can write. Okay, one can do several derivation, and one can find in the original paper this, but basically it ends up to be a term in which the correlation energy is related to the local polarizability of the 2 points with 1 over R6 dependence, and then if you integrate this, and then you make a crude approximation of the local polarizability, so some kind of local density, local polarizability density functionals in which the polarizability of a region of space is the integral of a local point-wise polarizability, which is related to the plasma frequency, and then the plasma. So in the end, it boils down to make an approximation of what the plasma frequency in each point is, and after some derivation, they end up to this equation, that is what we had before, in which this kernel function is a complicated object. something that depends on the point, on the plasma frequencies of the point, but in a complicated way, and how we are minus r prime sixth. And depending on, so different methods at the end differ for the choice that you make of omega 0. So if they were able to produce correctly some function as well, yeah, this is what I wanted to say. So depending on how you approximate the omega 0, yeah, if you choose this approximation, then you end up with the DFT. Then if you modify some parameter, you end up with DFT2 or another one, or VV10 has choose another options. But basically, they all based on that formula, just depending on which local polarizability you how you describe the local polarizability in terms of this omega 0 and which approximation you make for this omega 0. But there is a technical point associated to the fact that this is a six-dimensional integral, so in principle is expensive to compute. And then Roman Perez Soler introduced a interpolation scheme in which this functional phi that depends on omega 0 and of the 0.1 and 0.2. So they are, in principle, depends on four quantities, the density and the gradient and the 2 points. So this would be 4 points. However, the way they appear in the formula, they appear in groups. And so basically they depend on two variables that let's call it Q1 around R1 and Q2 around R2. And so therefore, one can write this kernel, one can expand on a basis of polynomials. And then by doing that, basically one can reduce the six-dimensional integral to a sum over a number of points on an interpolating grid of quantities that can be computed by convolutions, because Q alpha, Q beta here are parameters, and so for each set alpha beta, for each chosen alpha and beta, this is basically the is a convolution of R minus R prime between a density of R and a density of R prime. So this is something that you can calculate in reciprocal space, and so this is much more efficient. And so this is how van der Waals DF is implemented, for instance, in quantum espresso. We do this problem, and he is able to describe correctly the evolution of I don't know, some amino acid under pressure. And so we see, what do we want to see? That there are bad behavior at low pressure. Okay, when you pressurize, at the end, van der Waals doesn't count anymore because the fragments become in contact. But at low pressure, PBE is very bad. Rev PBE also has strange behavior. Instead, VDVDF or VDVDF with some other variant of the exchange do reproduce well the experimental. And okay, there was an extra problem when dealing with VV10 because the kernel has a different shape, which is actually simple, but it's not true anymore that omega, I mean, density and gradient enter in a combined way. So we need to do some trick, but we made it, so it's working. And then we have the revised VV10, which is a modification which basically is equivalent to the original VV10. And it and we use it for phonons in many systems, a few systems, but in particular graphite, and we are able to describe reasonably well the very soft modes of between the layers. So I stop here, and basically, okay, I briefly described the main semi-local functionals. The two problems that semi-local functionals do not address are self-interaction correction and van der Waals. They are two separate problems, and ways to deal with the self-interaction corrections have been hybrids and LDA plus U, which we hear more next days. And for van der Waals, it is a correlation effect, so should stay inside the chain correlation term. This is what VDVDF and VV10 try to do, but also a practical attitude that people have taken is to just take Tachenko-Scheffler or Grimm methods that add this empirical contribution on top of a semi-local functional. I stop here. I think. Oh, badly. Oh, no, I'm on time. Yeah, sorry. Yes.
So one question about proving non-local van der Waals.
Yes.
And generalization is polarized.
Okay.
So, from the papers of Konauter,
yes.
learned that RBD10, BB10, this family of functions cannot be really properly generalized in polarized case.
Okay.
While DW, DFT can. So what would be a comment of suggestion?
So my comment is that okay, so these the VDVDF family, let's say, compute the all correlation is described by this functional. So also, therefore, the the semi-local part, sense. And it is based on LDA. So there is no spin polarization there. And Tonhauser has then produced a new functional in which these things is taken care. VV10 instead is added as a correction on top of a normal functional in a certain sense, because try to describe only this fluctuation between different fragments. So in a certain sense, this, to the extent that this fluctuation effect is an electrostatic effect, is a time integrated, but is an electrostatic effect, then there is no spin, I would say. And so I would expect that VV10 on top of a spin polarized functionals is reasonable. Maybe it's not the ideal things, but I would expect it to give physical sense. Instead, if you use these functionals for a material that is magnetic, they don't have the semi-local part correct. So then you should use this new functional by Tonhauser, where he addressed exactly this problem. So, because basically VDVDF tried to describe the full correlation, so including, therefore, the LDA and GGA part, while VDV10 wants to describe only the bit that is not included in the semi-local part. So in this sense, if this bit is, as I think, due to density fluctuation, so there is no spin involved, maybe it's not perfect, but it should be reasonable. While if you do something that does not care, does not contain spin at the LDA and GGA level, then you are basically not describing that physics. And you should go to these more complicated functions that Timo Thunhauser has been developing in the last years. Okay.